Slopes of tangent lines. Now it's getting calculus-y in here. Okay, so we have a point, 2 comma negative 4, which mysteriously they drew above the x-axis. That bugs me a bit, but I don't think it's going to hurt us too much in this problem. The idea is we have the point P, and then we have another point Q, which is only a little bit away from that. The idea is that we move from 2 just a little bit to the right, so our new point's coordinate is 2 plus h. H as in horizontal distance. It's not a very big amount. This might be 2.1 or 2.01, but we've moved from 2 to somewhere a little bit to the right. What's our y-coordinate? Well, you can find it by just taking 2 plus h and subbing that into the function. And they have the function right up here, x squared minus x minus 6. So everywhere that you see an x in this expression, you have to put 2 plus h now. So we get, there's x squared minus x minus 6. Fair enough? Every place that used to contain an x now gets 2 plus h. And when we clean this up, we get, let's see, 2 plus h times 2 plus h is going to be 4 plus 4h plus h squared. Then we get minus 2, and then we get minus h, and then we get minus 6. And when we clean all that up, h squared plus 4h's minus an h is plus 3h. And 4 minus 2 is 2, minus 6 is minus 4. That's our y value. I'm just going to take that text and scoot it over here. That is our y coordinate. Fair enough? This isn't nice, but it's true. This says if you start at 2 and then you move a little bit over, your y coordinate will be, it won't just be minus 4 anymore, it'll be minus 4 with these 2 extra pieces on. These account for how much of a difference it makes to scooch over a small distance to the right. And they're asking for the slope of the tangent line, meaning the slope of the line between these 2 points. Because that line fits the curve fairly well, and it's going to fit the curve really well when we make this distance short. So if we can find the slope of this line, that's like finding the slope of the parabola. And we do that slope, just like any other slope, it's a rise over run, meaning it's y2 minus y1 over x2 minus x1, which, using these points, looks like the following. y2 is h squared plus 3h minus 4 minus y1 is just negative 4 over x2 is 2 plus h minus x1 is just 2. So if we clean that up, we get h squared plus 3h, let's see, minus 4 plus 4. So the minus 4 and the 4's just cancel. This is a negative 4. Here we get a positive 4, so those are gone. Over 2 plus h minus 2 is simply h. So when this all cleans up, it turns out our slope, sorry, I should say up here, slope equals, the slope is going to be h plus 3. Now, the last step is we've got these 2 points, they're distance of h apart, and this slope is a pretty good match for the slope of our curve. It becomes a perfect match if h is very small, if we let these points get infinitely close together. And we know how to do that now because we've done the limits unit. That just means let h go to 0. And so we get our slope is going to be the limit of, as h goes to 0, of h plus 3. You just plug that 0 in and you find that the slope at that point is 3.